Assalamualaikum and hi to Dr. Delhi. Okay, in this presentation, I'll show how we can use multivariable calculus to solve a real-world problem to optimize the shape of a satellite dish to focus signals accurately. This is a perfect example of how abstract math concepts have very practical applications in engineering and telecommunication. Okay, so the real problem is how to design a satellite dish that focuses incoming signals to a single receiver. Okay, let's define the problem. As we can see here, here's the satellite, one of the example. A satellite dish's job is to receive signals, typically radio or microwave, that travel as parallel rays from satellites in space. So, to collect this signal efficiently, the dish must reflect them toward a central receiver or sensor. If the dish is not shaped perfectly, signals may be misdirected, leading to weaker reception or total loss, which means it doesn't get the signal. So we need a shape that ensures every incoming ray reflects towards the same point, which is the focus. Okay, how to design the satellite dish? So as you can see here, signals arrive as parallel rays from a satellite in space, so the surface of the dish must reflect. And also, if there any error in slope or curve will cause signal loss. So, how to overcome the problem? So, we use the ideal shape, which is a paraboloid. Why parabol are used in dishes and similar technologies because it reflects all incoming parallel rays to a single point, which is used in telescopes, satellite dishes, and solar panels. Okay, so we can model the shape of the dish as z equals to the function fxy 1 over 40 x squared plus y squared. So this shape is designed so that all parallel rays that hit the surface, the parabolic surface, and converge at the same point. So this ideal shape that satisfies this condition is parabolic, which is a surface generated by rotating a parabola around its axis. Why? Why this shape? Because it has a special property. All incoming rays parallel to its axis reflect and pass through the same focal point. This makes it perfect for applications like satellite dishes, solar collectors, and even telescopes. So, what is the x? X and y represents the horizontal position in centimeter on the dish. So the function represents the height, which is the depth of the dish at that point. So this is parabolic, which ensures all parallel rays reflect towards a single focus. Okay, so when I use GeoGebra 3D calculator and I typed the input, the function that I just said just now, fxy 1 over 40 x squared plus y squared, and also the range, then the model of the surface is built in the 3D calculator. So we can model the surface of the dish using a function of two variables, like I said just now, and the limit is x squared plus y squared lesser or equal to 100 to shape the realistic circular dish of radius. So all the engineers can use it to uh, create the exact parabolic shape of the satellite. So this represents the dish surface in 3D space. Okay, the range is x squared plus y squared lesser or equal to 100. Okay, why do derivatives matter? So the rate of change of the surface curved the dish is at any point. So this is important. Focus the signal precisely at the receiver. We use derivatives. We compute partial derivatives, which becomes the function becomes x over 20 and y over 20. So these tell us how steep the surface is in the x and y directions. If we set the function k, we get x squared plus y squared equals 40k, which are circles in the xy plane. As we can see here, this shape is formed. The deeper the curve, the stronger the signal focus. And also, okay, as you can see here, these are some useful visuals to see how the height changes. This slope is the gradient vector, which combines the two directional rates to change into a vector that points in the direction of steepest ascent. Its components show how much height increases per unit movement in x and y direction. The magnitude of this vector tells us the overall steepness. So after I key in the input x over 20, then we get the plane. Okay, and then for the next one, this is the gradient vector field of the satellite dish surface. The arrows show the steepest direction of surface slope at each point. These slopes help engineers calculate how incoming satellite signals will reflect toward the focus point. Similar to the bowl, just like a bowl, the further from the center, the steeper the slope, crucial for designing signal direction and strength. Okay, so for this part, okay, back to the before. This one will help engineers to visualize how to shape the dish at every point. Okay, now let's apply this one point here, point B, which is x is 6 and y is 8. And then after substituting into the function, we will get 2.5 centimeters. So the height is 3.125. At point B, which is 6x and y8, we get a gradient vector and height of 2.5. So, which means point B lies exactly on this dish edge. These examples show how the slope varies across the surface and how we can use calculus to predict and optimize the shape. So, what is point B? Point B is a spot on the edge located x equals to 6 and y equals to 8 and will form z equals to 2.5. So, which means it helps to determine how tall the edge of the dish is compared to the center. In this case, 2.5 centimeter, right? So, meaning the dish curves upward just enough to reflect signals efficiently. This height is important for ensuring signals reflect to the focal point without overshooting or scattering. So, engineers use these boundary points, like point B, to verify curvature, shape the outer ring of the dish, maintain symmetry for full 360-degree signal capture. Even a small error at the rim can cause signals to miss the receiver. So, this shows the rate of increase in height at that point, essential for shaping the reflective surface angle. So, the dish shape must redirect all parallel signals to one focal point. Points like B ensure that even edge reflections are precise and maximizing signal strength and minimizing interference or data loss. So, for the conclusion, if any section of the dish is too deep, hmm, apa dah? If any section of the dish is too steep or too shallow, the signal may not reach the receiver with uh, good calculations. We can precisely shape the surface and avoid signal. This is where calculus meets engineering. So we've looked at a real world scenario and used multivariable calculus to understand and solve it. From modeling to solving and visualizing, every step relied on calculus. Thank you. I hope this can, I hope this makes, makes us understand how maths can help us learn in theory becomes the foundation for technology all around us.